Well, hello again everybody. As you can see, I've finished off the build of this little FM transmitter and it really didn't give me any problems. I think that where I left it last time, we just had these 3 transistors to install, and maybe we had the variable capacity in the electric mic, but it all went in very smoothly. I didn't really have any construction problems with it. It was a nice little kit to build, and I'd recommend it. Now, when I was googling around, I did find a number of comments where people were struggling to install this little condenser microphone here, and it's a 2-pin device, and the problem that everybody was having was that they didn't know which way round to put it. From memory, there is a little positive symbol marks on the board, but you can't see now because it's underneath the component. But there's 2 legs on these and neither of the legs are marked, so which one is positive? Well, the way you find that out is pretty simple. All you've got to do is you've got to use your own meter, set it to continuity, and if you take a continuity reading between the metal body of the condenser mic, and each of the legs, you will find that one of the legs is connected to the metal can. Well, the one connected to the metal can is a ground connection, is a screen connection. So that's how you determine it. Now, it's actually a little bit tricky to find a good circuit diagram of this online, and this is the one that was on the vendor's website on eBay, but you can see there's actually no component references on here. But I did actually find another circuit online just by googling round, and that's this one. But unfortunately this circuit, I think it's meant to be exactly the same device, but unfortunately whoever drew it got it wrong, so I've actually had to modify it a little bit. They'd actually missed off some of the components, which is they'd missed off this padding capacitor here, and I think they'd also missed off the variable capacitor. In fact, it's actually I think they've actually got a reference there, adjust slug tuning coil. Well, it doesn't have a slug tuning coil, it has a variable capacitor. So I've gone away and I've just redrawn this bit of the circuit, and I've also just gone ahead and I've just roughly worked out what some of the inductances is for the various coils, because it just says things like 8 turns or 4 turns or stuff like that. So I did just go away and for my own interest as much as anything, I've just gone away and just roughly estimated what some of these coil values are. I'm not saying they're bang on, but they're probably in the ballpark. Well, if everything looks and sounds a little bit different, it's because I'm using one of these little happy snappy cameras, so I'm not sure if the audio is going to be any good. But it's all I've got, so we're just going to have to crack on with it. So let's start off at the front of the circuit where we've got this little condenser microphone. And you can see here we've got a 4K7 resistor. Well, the reason that we've got a 4K7 resistor, and it's actually feeding a power supply to the condenser mic. The condenser mic is actually just a variable capacitor, and they're actually capable of quite high voltage outputs from a condenser mic, but unfortunately there's absolutely no current, unlike a normal dynamic microphone that has got a moving coil and a permanent magnet, which can actually produce reasonable voltage and current output. A condenser mic can't produce any current output, so what you have to have internally, they tend to have a little field effect transistor which acts as a buffer, and they need a power supply, so that's what this 4K7 resistor is doing. I think some people call them, don't they call them ghost supplies or something like that. So that's all this 4K7 resistor is doing here. It's actually powering up the little internal circuit in our condenser mic. Now, when I was assembling this little circuit board, I think I did touch on the fact that you've got to get the condenser mic the right way around. So you can see here that one leg is connected to the to 0 volts, and the other one is being pulled up to plus VCC. So you have to get the microphone connected the right way around, or the little the FET transistor won't be powered up and you won't get any audio out of it. So yeah, you've got to get them in the right way around. So the condenser mic is AC coupled through this little 100 nanofarad capacitor here. So the fact we've got a 100 nanofarad capacitor means that we're not exactly in the realms of high fidelity, are we? And we've got this little transistor amplifier, and I think I've labelled that Q1 there. So the first transistor here is a little audio preamplifier, and it's very crudely biased into Class A mode. I did actually plug the scope into the collector point here, and it's approximately half VCC. So basically what that means is we're in Class A, because any audio input that we get here, this transistor is going to be conducting through the full 360 degrees of the input waveform. So that's why we call it, well, that is Class A mode. So if you look at the collector here, that's approximately 2 volts, which is it's half VCC. I say half VCC, I was actually running it at 4 volts when I did this test, and I think it was about 1.9 volts or something like that. And the transistor's actually being biased by this 1 meg resistor, but you can see it's actually quite interesting the way that this bias works. Of course, it's quite common on a transistor amplifier to require some negative feedback, and you'll normally find that negative feedback is provided by an emitter resistor here. Well, we don't, as you can see, we don't actually have an emitter resistor. We've only got this bias resistor here, which is collected to the connector, but it actually works in a not totally dissimilar way. So basically, as this transistor conducts more and more current, the voltage at this point here will start to fall because it's being fed by this 10 kilo ohm. So as this transistor turns more on, the voltage here will fall, and because the voltage there is falling, the bias level here will also fall, the voltage and current being applied to the base of the transistor. So effectively that's, although it may not look like it, that's producing some negative feedback. We said we had our horrible little pinky LED, so that's just all this circuit here. So we've got a 4K7 resistor, and that's just wired in series to our little pinky LED, and the other side of that is connected to ground. So we get our amplified audio, and that's passed on to the next stage by this, again it's AC coupled using this 100 nanofarad capacitor, and then we've got this connector here, this input audio jack. So what you can do is you can actually choose to get the audio input from the microphone there, or we can also get an audio input just by plugging in a little jack connector. If you plug the jack connector in, it does something quite clever in that it actually disconnects the audio from this point. Hopefully you can see that there's a little switch contact in there, so when you put in an external audio supply, it disconnects the microphone and then it feeds audio straight into the next stage. So the next thing in our circuit here, we've got a little 10k volume pot, so that's a little variable potentiometer. Where's that? Oh yeah, that's there, that's a little volume pot control. And then that's being, again, got some AC coupling here. Now of course this is a transmitter, so we actually need a source of RF, radio frequency oscillation, and that's actually being generated here by Q2. And what we've actually got is we've got a simple Colpitts oscillator, which really consists of this L1 here, which is, where's L1? There's our L1 there, that little inductor. Is it L1? Yeah, it is. So there's our little inductor, and that's in parallel with this 24 picofarad capacitor, which is the one, I think that's the one just in front of it there. So you can see that this inductor and this capacitor, they're in parallel with each other, and that forms what we call a little tank circuit. So that's going to be resonant at a certain frequency, and that frequency is going to be somewhere in the FM band. So I'm going to say let's say it's going to be resonant at 100 megahertz. But because we want to have a little bit of adjustment over that range, we've got this little variable capacitor here. So again, so this variable capacitor is in parallel with this 24 picofarad. I'm not sure what the value is of this this variable capacitor. I'm going to say it's going to be something pretty small, but what that'll allow us to do is it'll just allow us to pull the frequency of this tank circuit slightly in one direction or another. So we've got our inductor L1 and these two capacitors, and as I said, these form a little tank circuit. And I'm sure everybody knows if you actually kick a tank circuit, if you provide an electrical impulse to it, what you will find is it will resonate, and it will resonate at its fundamental frequency. But the problem is that frequency will reduce in amplitude. After you kick it, it will get smaller and smaller and smaller and peter out. So what you've got to do with a tank circuit, you've got to keep giving it a little tap. It's like ringing a bell. Though the way you actually ring the bell or you kick the tank circuit is you've got to provide some positive feedback. And the way that feedback is being provided, it's being provided here by this this connection to it. This is our positive feedback. So again, the tank circuit will oscillate. That will get amplified by the base of this transistor, which will make a bigger swing in current here, which will get fed back through these 30 picofarad capacitors and that 15 picofarad. It'll get fed back into the tank circuit, and it'll just maintain the oscillation. So that's our little oscillator there. It's all well and good having a carrier wave, but we actually need to modulate that, and we need to frequency modulate it. And we're going to frequency modulate it with our incoming audio because this is an audio transmitter. So if we just look at our circuit here, we can see the base and we can see the emitter, and of course we've got a base emitter junction. What might not be so clear is that when you get one of these silicon junctions, you actually form a capacitor, and the capacitor is it's between the base and the emitter. Maybe I should just draw it in. Let's just draw in a little capacitor there. You have a capacitor which is going across the base and emitter junction. It actually varies this capacitance, and what it varies with the voltage which is across the base here. So if you get, I think it's if you get a bigger voltage across here, I think the capacitance slightly increases, and I think if you reduce the voltage, the capacitance reduces. I'm not dead sure, I could have it completely the wrong way around. As our voltage here goes up and down, being driven by our audio input, the capacitance is going to change. And I think what's happening is this capacitance across here, it is effectively, it's rudimentally, it's in parallel with our tank circuit with these capacitors here. So as this capacitance varies, it's also going to slightly change the resonant frequency of our tank circuit. So I'm guessing that's how the FM modulation is done. Maybe you agree with that, maybe you disagree with that. If you understand the circuit better than me, by all means leave it in the comments, tell me what you think. But that's how I think the FM modulation is done. I think it's done by the varying base capacitance of this transistor here. So at this point here, which is the collector of Q2, we're going to have both the carrier, which is being modulated via our audio frequency waveform. So we've got everything we need there, but it's going to be a very low level signal. So what we need to do is we need to amplify it. So Q3 is our RF power amplifier, and the output from the power amplifier, again, it's coming from the collector here, and again it's being decoupled by a capacitor. And you can see here that we've got some other components here. So we've got two capacitors and we've got an inductor, and what you call that's actually a pi filter. It's a Chevy pi filter, and what that's actually doing, it's doing a couple of things. It's doing some impedance matching between the antenna and the actual output of our transistor Q3, but more importantly it's doing a low pass filter. So whenever you modulate a signal, and depending if you modulate a carrier by too much in the FM world, you produce a lot of high frequency harmonic contents. Those are undesirable. So what I'm basically saying is, if we design our transmitter to be working at 100 megahertz, you will find that it will also be outputting some power at 200 megahertz, which is the second harmonic, and it will also be producing power at the third harmonic. In fact, it'll produce power infinitely on all the harmonic frequencies, but you know, it tails off as you increase in frequency. The harmonic content reduces in amplitude. But for example, if we're designing our transmitter to work at 100 megahertz, we don't really want to be transmitting at 200 megahertz as well. So what this pi filter, and they call it a pi filter, what this pi filter is doing, it's a low pass filter. So this will have been designed to pass, for example, 100 megahertz, but it will impede the flow of frequencies at 200 megahertz or 300 megahertz. So it's a low pass filter. It's designed to pass 100 megahertz, but nothing above that. And the higher the frequency above the 100 megahertz, the more attenuation this filter will have. So hopefully you can see, here's our little pi filter here, so you can see the two capacitors. There's one capacitor there, there's the other capacitor there, and there's the inductor, which is strapped between them. And again, we mentioned this radio frequency choke here, RFC. That's our radio frequency choke, which is L2. So the output from our pi filter here, it just comes out on this length of brown wire, and it says here that it suggests you use 10 centimeters. So there you go, as normal, there's my very crude description of how this FM transmitter circuit operates. So I've just gone ahead and switched our little transmitter on, and we're rewarded by a little red light here, and you can see a little line has appeared on our spectrum analyzer. So just to prove that, I'll just disconnect it. The line's gone away and now it's come back again, and all I'm doing is I've just got a little antenna here which is connected to the spectrum analyzer, and I'll just turn it in the right orientation. We've got our being technical, at the moment you can see that we've got the antenna here and that's lied horizontally. So if we want to pick up the maximum amount of signal, this is, you might have heard about vertical and horizontal polarization. Well, here's a good example. Let's vertically polarize our antenna here. So we've vertically polarised the antenna, i.e. we have it sticking straight up. You'll see we hardly pick up any signal whatsoever, but if we put our receiving antenna in the same orientation as our transmitting antenna, which is this piece of brown wire, you might not be able to see that because my bench is brown, but there's a piece of wire here. If we actually put that in the same orientation as a transmitting wire, we pick up much more signal. Now this is why it's important, if you ever have to set up an aerial, you need to know what the orientation of the transmitting aerial is. You need to know, is it horizontally or vertically polarised, because if you get it wrong like that, you won't pick out, you'll pick hardly any signal up. So you need to get the polarisation right. So hopefully you can see that we're transmitting at 90 megahertz, and that's just being indicated here because I've set up a little mark here which is just tracking our little RF output. So if our circuit's working correctly, we should actually be able to adjust this little trimming capacitor here, and that should actually affect the transmitted signal. So let's just go ahead and do that. So you can see I've got a little bit of adjustment there. So what I was doing there, I was just affecting the capacitance of our little oscillator tank circuit. Now of course the tank circuit doesn't just consist of the capacitor, it also consists of the inductor L1. So if I basically just finger this inductor here, I'm just going to try and change the inductance by just spreading the coils. So I'm just going to stick my finger in there and hopefully we should be able to do the same thing. Can you see that I'm moving it to one side? Moved it a little bit, didn't I? I'll just squeeze it back together and then I'll let it go again. So you can see that as I just manipulate the inductor, that also just changes the frequency that we're set to. Now of course it's all very interesting to look at the spectrum analyzer, but we actually want to hear it as well. We want to actually see if our little FM transmitter is actually transmitting any audio. So to do that, let's just use this little scanner. So let's switch this on. Turn the volume up, and maybe you can hear something already. Oops, we're getting feedback. Yeah, that's not very nice, is it? So let's just prove that by beating hell out of it. Now something quite interesting happens next if I actually turn the transmitter off. So let's just disconnect the power. And what actually happens is, hopefully you can hear, there's a station in the background. So unfortunately my little FM transmitter here is actually tuned to over the top of some other station. Now I'm actually sure that this is such a low power transmitter, it barely escapes the house. It isn't actually going to be interfering with anybody. Now of course we shouldn't be transmitting the FM broadcast band at all, but you particularly don't want to be transmitting over another station, because if your neighbour, for example, wants to listen to that station, the local, even though this is a very low powered transmitter, because it's much closer to his radio than maybe the transmitting mast is, he's probably going to pick up your little FM transmitter as opposed to, his radio 2 that he wants to listen to. So you want to avoid transmitting on top of other stations. So what we want to do is we want to find a little bit of the radio spectrum which is free, and then we're going to tune our little FM transmitter to that. So just using my radio, I've just scanned round and I found that in my location we haven't got any stations. I can't really pick anything up around the 100 megahertz range, so that seems pretty free. And the FM band is actually pretty busy, but there is actually a bit of a gap here around the 100 megahertz. So what we'll do is we'll just go ahead and we'll just tune our little FM transmitter to 100 megahertz. So we're at 90 at the moment, so we're just going to go up. A bit more. Okay, so we're just over the 100 megahertz point there. And I think we'll just have to go ahead and retune our radio. And yeah, we're in the ballpark, 102, 102 on here. 1, 2, 1, 2, 1, 2. 1, 2, 1, 1, 2. So I've just moved our radio scanner into another room because you won't be able to tell the difference between me speaking into the transmitter and just the camera picking up the audio. So I've moved our receiver into the other room, and I'm going to go back into my workshop and shout some abuse at you, and you can tell me if you can hear me.
So I think we're following the footsteps of Alexander Graham Bell by repeating his first words, which were, "Watson, Watson, come here, I want to see you," as I've just dropped a beaker of hydrochloric acid on my bench.
Now in terms of deviation, this little transmitter is a little bit of a nightmare. As you can see, it's actually just basically going off scale on the analyzer. There's so much deviation I can't analyse it. I'm just going to have a go at turning the volume adjustment pot down because that could help. 1, 2, 1, 2, 1, 2, 1, 2. 1, 2, 1, 2, 1, 2, 1, 2, wallow, wallow, wallow. It's pretty much impossible here when you try and adjust the volume control pot to actually limit the deviation. You've basically got all or nothing and really not anything in between it. I wanted to just get a sample of the RF into the oscilloscope so I could just look at what the transmitted waveform looks like. So all I've got is basically I've got the scope probe, I've got the ground clip, and all I've done is I've wound the ground clip a few turns around this antenna, and what that'll do is it'll just take a little sniff of RF energy off this antenna. So at first glance you can see quite a nice sine wave, and as I'm sure everybody will know, that if you get anything less than a perfect sine wave, that will indicate the presence of various unwanted harmonics being produced. But what I will say is to look at it on the oscilloscope like this isn't a good test. You will find that even though the sine wave looks pretty perfect, there could actually still be quite large harmonics being produced. You won't actually see any distortion of the sine wave until the actual harmonic contents is pretty horrendous. So of course the best way to look for harmonics is actually to use a test receiver to actually just scan through the bands where they might be occurring, or if you're lucky enough to own a spectrum analyzer, to use that. So let's do that. So here's our spectrum analyzer just displaying our FM carrier. It's around 100 megahertz. Let's have a look at the second harmonic that's going to be around the 200 megahertz point. So frequency 200 megahertz. This is a little bit of a dirty test because what you should really do is you should actually use a filter connected to the front end of your spectrum analyzer, and really if you were doing this test properly you would actually want to filter out the fundamental, because then you can increase the dynamic range on your spectrum analyzer and see the very small low level signals. But this is a quick and dirty test. Now I can't see anything there. I can't really see any peaks. All I can see is a lot of background noise. What we can do to maybe help pull the signal out of the background noise is we can just put some filtering on. So now we've switched on some of the averaging, you can actually see that some signals have been picked out from the noise. You couldn't see them before because we were right down at the noise floor of the spectrum analyzer, but I've just turned up the averaging and you can see a couple of signals have appeared now. Now I'm not sure if they're real or not, but one of the things that we can do is let's just turn our transmitter off and see if they disappear. Now I think you'll see that one of them still remains, so that little peak there, that's something in the room. Let's turn the transmitter back on. But we have got another little runt there appearing there. Let's just see what frequency that's at. Yep, so that's at 200 megahertz, which is exactly where we would see our second harmonic. But it's still quite a long way down that. I think it's, I can't remember what the other level was before. I suspect we're about 40 dBs down on our carrier. I mean, obviously you'd want to see more than that in a perfect world. You'd want to see it at least 60 dBs down, but this looks like this little low pass filter is doing its job. Let's just see if we can see anything at the third harmonic, because they can be problematic. So the sensor frequency of our spectrum analyzer has now been set to 300 megahertz, so that's this line here down the centre. So we might be expecting here to see this third harmonic, but I can't actually see anything. We've got our second harmonic back here somewhere. I think that might be the remnants of our second harmonic, but Yeah, there might be a little bit of something there, but it's pretty small. Now I realise that quite a lot of you aren't going to have a spectrum analyzer on your bench. Well, don't think that lets you get away with not checking for these harmonics, because the other way we can do it is just to use a receiver. So, you know, this is something you might have, just another radio receiver. You probably do want a scanner, because we need to go, you know, up in the frequency range, something that, you know, an ordinary domestic broadcast receiver probably won't go to. But I think this is a reasonably good one, and it goes to over a gigahertz. So I'm going to just try tuning in around the 200 megahertz to see if we can pick up that second harmonic. So let's just let's do that. 200. So I've gone ahead and set our scanner to 200 megahertz now, and you can probably hear there is a little bit of something, but yeah, that's not totally abnormal. You'd kind of expect that with any transmitter, even a radio ham transmitter. You're going to pick up a tiny sniff of second and third harmonics and stuff like that, so that's not really anything to worry about. So we are picking up a little bit of our third harmonic. I can just hear it being picked up at just over 300 megahertz, but the reality is that's actually a pretty pointless test, because this circuit itself, it's not in a screened enclosure, and this is a very, very sensitive receiver. So the reality is we're actually probably picking up the harmonics from the circuit board itself before it even reaches this little this little low pass filter. So that was all probably a little bit pointless, that test I did there. But I guess the point was just to know that when you build a little transmitter, in fact any transmitter, it doesn't just transmit on the frequency that you're intending it to. It will actually transmit on multiples of the harmonic of the main fundamental frequency.